In this video, I will write two proofs for the same theorem. The two proofs are completely different, but they are both equally valid. Here is the theorem. I want to show that the sum of the first n positive integers, 1 plus 2 plus 3 all the way to plus n, equals n times n plus 1 over 2. And I want to show this is true for every positive integer n. I like this theorem because we have a choice on how to prove it. The statement depends on a positive integer n. And therefore this is a good candidate for induction. And in fact, there is a nice short proof by induction that works very well. That will be my second proof. But we also can do a nice direct proof without using induction at all. That's going to be my first proof. I'm going to give a name to this sum. I'm going to call it Sn. So Sn is 1 plus 2 plus 3 plus ... all the way up to plus n. And underneath, I'm going to rewrite the same sum, but I'm going to reverse the order of the terms, starting at n. So Sn can also be written as n plus n minus 1 plus n minus 2, ... all the way down to plus 1. And then, the trick is going to be to add both lines. On the left-hand side, I'm going to have Sn plus Sn, which is 2Sn. And on the right-hand side, let's group the terms. 1 plus n is n plus 1. 2 plus n minus 1 is also n plus 1. 3 plus n minus 2, that is also n plus 1. And all the other pairs of terms, when I group them this way, add up to n plus 1 as well. This is a nice surprise. I have a total of n terms, and every term is n plus 1. So 2Sn must be n times n plus 1, which means that Sn is equal to n times n plus 1 over 2, which is exactly what I wanted to show, and we are done. Notice that this was a direct proof. There was no induction or anything else. The proof works fine for all values of n at once. I didn't assume anything at all. I simply used algebra without assuming anything and end up concluding what I wanted to prove. Now, if we prefer, we can also try to do a proof by induction. It's a statement that depends on n, so it's prepare for it. That's going to be my second proof. I have written explicitly that this is a proof by induction, since otherwise my reader will not know what I am doing. Like all proofs by induction, it has two parts. First is the base case. For this theorem, n equals 1. When n equals 1, what do I need to show? That the sum of the first one positive integer, so that's just 1, is equal to this expression when n equals 1. Let's simply write that down. And yes, this is true. Just check the calculation. The induction step will be more interesting. First, I will fix a positive integer n. And then for that value of n, what I need to do is assume this equation is true for that value of n, and try to prove that the equivalent equation, when I use n plus 1 instead of n, is also true. So I am assuming that 1 plus 2 plus 3 all the way down to plus n is equal to n times n plus 1 over 2. And I want to show that the same expression is true when instead of n, I put n plus 1. So on the left-hand side would be 1 plus 2 plus 3 all the way to plus n plus 1. And on the right-hand side, it will be this fraction when I use n plus 1 instead of n. Now, how do I go from this equation to this equation? What I can notice is that in the second sum, what I have is the same as the first sum plus an extra term. And that's it. That's all I need to notice. So I'm going to write that 1 plus 2 all the way to plus n plus 1 can be broken as the sum of the first n terms plus n plus 1. And now I simply get to use my assumption. By induction hypothesis, I can rewrite the sum of the first n terms as n times n plus 1 over 2. And the rest is algebra. All I need to do is reduce to common denominator and add up the two fractions. And I managed to prove exactly what I wanted to show. So that completes the proof. There we have it. Two very different proofs for the same theorem. To summarize, we wanted to prove that this equation was true for all positive integers n. The first proof was a direct proof. We managed to find a trick that allowed us to prove it for all values of n at once. The second proof was a proof by induction. I only proved it for one value of n equals 1. But then I also proved that if the equation was true for one value of n, then it must be true for the next value of n. And those two things together implies that the equation is true for all positive integers n. Which proof is better? They're both equally valid, so it's a matter of taste. Which one do you prefer?